love this topic because people have these wonderful romantic ideas about what space travel is going to be like. They imagine sleek spacecraft zooming between the stars, beautiful planets, alien civilizations greeting us with open arms. But then when you actually do the calculation, when you actually think about what the physics tells us, it's kind of terrifying. And that's what I want to talk about today. Let me start with something very simple. You see that star up there at night, the brightest one after the sun? Well, most people don't realize that the nearest star to us, Proxima Centauri, is about 4¼ light years away. Now you might think, well, that doesn't sound so far. Light travels at 186,000 miles per second. It's the fastest thing in the universe, right? And it takes light 4¼ years just to get there. Think about that for a moment. Light, the fastest thing we know about, 4 years. Now let me ask you something. What if I told you that our fastest spacecraft ever built, the Parker Solar Probe, would take somewhere around 75,000 years to reach Proxima Centauri? Not thousands of years, not hundreds, 75,000 years. Do you understand? We're talking about a period of time longer than human civilization has existed. If we sent a spacecraft right now, it would arrive long after every human being alive today is gone, and their great, great, great descendants for hundreds of generations into the future. That's the scale of the problem. And it's not a human problem in some abstract sense. It's a physics problem. It's a real, concrete, mathematical constraint that comes from the laws of nature themselves. Now, someone will say, but wait, we don't have to go that slow. We can go faster. And they're right. Theoretically, we can. But here's where it gets interesting, or rather where it gets impossible, depending on how you look at it. To reach Proxima Centauri in a reasonable time, let's say in 40 years, which is a human lifetime, you would need to travel at about 10% the speed of light. 10%. That's 18,000 miles per second. Now, how do you do that? What do you burn? What's your fuel? Let's think about chemical rockets, the kind we use today. An Apollo rocket, our fastest traditional rocket, produces thrust by burning hydrogen and oxygen. It's a marvelous machine. But the physics of chemical combustion has a limit. It doesn't matter how clever you are, how good an engineer you are. The energy density of chemical fuel is fundamentally fixed by the laws of chemistry. And that energy density is not nearly enough to accelerate a spacecraft to 10% light speed. So people say, okay, what about nuclear propulsion? And nuclear energy is much more dense than chemical energy. Nuclear reactions release tremendous amounts of energy. But here's the catch, and this is the beautiful part. When you do the calculation, when you actually sit down with the equations and work it out, you find that you would need to carry fuel with you that weighs so much that the rocket becomes impossibly huge. It defeats the purpose. Let me give you a simple way to think about this. Imagine you're building a space shuttle. You put fuel in it. That fuel weighs a lot, so you need more fuel to move the fuel. But that additional fuel weighs more, so you need even more fuel to move that fuel. And this cascade continues until you find that you need more mass and fuel than would be practical to ever construct. This is called the rocket equation, and it's a fundamental constraint. Now, there's a theoretical solution that physicists like to talk about called antimatter propulsion. And this is where it gets really interesting, because antimatter is truly remarkable. If you take matter and antimatter and they touch each other, they annihilate. They convert completely into energy. Einstein's EMC2 tells us that even a tiny amount of mass contains an enormous amount of energy. So theoretically, antimatter could provide the energy density we need. But here's the problem. We can't make antimatter in useful quantities. We can create a few particles of antimatter in high-energy particle accelerators, and we can only hold them in place using extremely powerful magnetic fields. And the amount we can make is infinitesimal compared to what we'd need for a spacecraft. Plus, storing antimatter, that's like trying to store an atom bomb. One mistake, one failure in the magnetic containment, and you have an explosion equivalent to a nuclear weapon. So antimatter, while theoretically interesting, is practically impossible for us to use anytime soon. Maybe in 1,000 years if we figure out some new physics, but we're not there yet. Okay, so what about the theoretical ideas? You know, warp drives, wormholes, these things that physicists talk about sometimes, and I have to tell you, as someone who thinks deeply about physics, these are fascinating intellectual exercises, but they're not engineering solutions. They're not even close to being engineering solutions. A warp drive, like the Alcubierre drive that people talk about, would require something called exotic matter. This is matter with negative energy density. Now, negative energy does exist. There's something called the Casimir effect that demonstrates it on a tiny scale. But we're talking about needing planetary amounts of negative energy. literally the mass energy of Jupiter or Saturn of negative energy, to warp space-time around a spacecraft. We have no way to create that. We have no way to contain it if we did create it. And even the theoretical physics isn't worked out enough to know if it would actually work. It's a bit like saying, well, if we had a perpetual motion machine, all our energy problems would be solved. Yes, that's true. But perpetual motion machines violate thermodynamics. And these exotic solutions violate our current understanding of what's physically possible. Now let's say, just for the sake of argument, that we somehow overcome the propulsion problem. We figure out a way to accelerate a spacecraft to 10% the speed of light. What happens then? Well, now you have other problems that are just as deadly. For instance, there's the cosmic dust problem. Space isn't empty. It's filled with tiny particles of dust and ice. At 10% light speed, these dust particles become projectiles. A grain of sand hitting your spacecraft at 10% the speed of light carries the kinetic energy equivalent to a bullet. It would punch right through your hull. Multiple impacts would destroy your spacecraft completely. So you need shielding. But shielding is heavy. The heavier your shielding, the more fuel you need to accelerate the spacecraft. And we're back to the rocket equation problem again. It becomes a vicious cycle. There's also the problem of radiation. Space is not hospitable. It's filled with high-energy cosmic rays. Without Earth's magnetic field to protect you, you're exposed to constant bombardment by particles that can damage DNA, cause cancer, damage the central nervous system. If you're traveling for decades or centuries, the cumulative effect of radiation exposure is devastating. Your crew would get sick. They would develop cancers. Their cognitive function would be impaired. It's not a quick death. It's a slow, horrible deterioration of the human body. And let's talk about the psychological effects. You put people in a spacecraft. It's a confined metal box. They're traveling away from Earth, away from everything they know for years, decades, maybe centuries. The isolation is profound. We know from studies of Antarctic researchers and submarine crews that human psychology cannot handle extreme isolation for extended periods. People become depressed. Relationships break down. Some people become violent. Some people become suicidal. Now, if you send a small crew, maybe 10 or 20 people, you have another problem. You can't maintain genetic diversity. You can't avoid inbreeding. If you send 1,000 people, then you need a spacecraft so large that the engineering challenges multiply exponentially. You need life support systems that are incredibly reliable. You need to grow food somehow, recycle water, recycle air, keep everything running perfectly for hundreds of years. And here's something people don't think about. What if the spacecraft fails? What if something breaks that you can't fix? Once you're halfway to the next star, you can't turn around and go home. You can't call for help. There's no help. You're committed. You're going to die out there floating in the black, your spacecraft slowly degrading around you. This is why I call it a suicide mission, because that's what it is, realistically speaking. You're not going to survive. Your grandchildren probably won't survive. Maybe your great-great-great-grandchildren will arrive at the destination, assuming the life support systems hold together for that long. Now, there's an idea that some scientists have proposed. They call it a generation ship. The idea is that you send a spacecraft with thousands of people, and they live their entire lives on the ship. Then their children live their entire lives on the ship, and their children's children. Over the course of centuries or millennia, eventually the ship arrives at another star system. But think about this carefully. What do you do for governance? Do you have democracy? If you do, people will vote to turn around and go home. But you can't turn around. You don't have the fuel. So you have to have some kind of authoritarian government that forces people to stay on course. What does that do to the human spirit? What does that do to the culture and the psychology of the people on board? And there's another problem. Technology changes. What if 100 years into the journey, someone on Earth figures out a way to travel much faster? A new propulsion system that can get to the next star in 50 years instead of 200. Well, they'd send a new spacecraft. It would arrive first. The generation ship would arrive a century later to find that their destination has already been colonized, that they're not pioneers anymore. They're redundant. And what about the people left behind on Earth? Who pays for this? Who maintains the infrastructure to launch a generation ship? A generation ship would cost more than the GDP of most countries. It would require a stable civilization that can maintain the commitment for centuries. One world war, one climate catastrophe, one serious economic collapse, and the project gets abandoned. The generation ship is left without support, without supplies, without hope. I think about this, and I realize how profoundly difficult this problem is. It's not just an engineering problem. It's a biological problem. It's a psychological problem. It's a social and political problem. It requires solving multiple impossible problems simultaneously. Now, some scientists say, well, what if we don't send people? What if we send machines, robots, artificial intelligence? And this is actually a more promising idea, I think. A small robotic probe, maybe just a few kilograms, could potentially be accelerated to a significant fraction of light speed. A team at the Breakthrough Initiative proposed something called Breakthrough Starshot. The idea is to use powerful lasers to push tiny spacecraft only about the mass of a postage stamp to about 20% the speed of light. With 20% light speed, you could reach Proxima Centauri in about 20 years. And this is actually technologically feasible. It doesn't violate any laws of physics. The engineering is difficult, but it's not impossible. You'd need a laser about 65 gigawatts. That's a massive amount of power. But we know how to generate that much power. You'd need the spacecraft to be incredibly light and incredibly durable. You'd need perfect aim. But these are engineering problems, not physics problems. The catch? The spacecraft would be unmanned. You'd get data back, you'd get pictures, you'd get information about the planet around Proxima Centauri, and that's valuable. That's genuinely valuable. But you wouldn't get people there. You wouldn't establish a colony. You wouldn't have humans living on another star system. And that matters to people for some reason. They want humans out there. They want to colonize. They want to expand. But the physics doesn't cooperate with our desires. The physics just tells us what's possible. Now let me address something people ask me. They say, but what about relativistic time dilation? Einstein showed that time slows down when you travel at high speeds. So if you travel at very high speeds, you could experience less time while centuries pass on Earth. And this is true. Einstein was right about this. If you traveled at, say, 99% the speed of light, relativity tells us that time dilation effects become significant. You might experience only a few years while centuries pass on Earth. But here's the thing. Getting to 99% the speed of light requires even more energy than getting to 10% the speed of light. You need even more fuel. You need even more thrust. The problems get worse, not better. Plus, there's something called the Lorentz contraction. At very high relativistic speeds, distances contract in the direction of motion, so space actually gets shorter from your perspective. But this doesn't mean you get there any faster in real time. It's just a geometric effect. It doesn't change the fact that you need enormous energy to accelerate. And there's one more thing. When you arrive at your destination, you need to decelerate. Getting there in a few years doesn't matter if you're traveling at 99% light speed and you have no way to slow down. You'd hit the destination planet at near light speed and everything aboard would be vaporized instantly. So relativistic time dilation is interesting from a theoretical standpoint, but it doesn't solve the fundamental problem. It doesn't make interstellar travel practical. It just highlights different aspects of the same impossible challenge. You know what I think is interesting to consider? The possibility that this is the answer to the Fermi paradox. Enrico Fermi looked at the night sky and asked, if there are all these stars and many of them have planets, where is everybody? Why haven't we been visited by aliens? And one answer is, maybe interstellar travel is just too hard. Maybe the physics doesn't permit it. Maybe every civilization that develops space travel runs into exactly these same problems. The distances are too vast. The energy requirements are too enormous. The travel times are too long. The engineering challenges are too many. And so civilizations like ours look up at the stars and realize they're unreachable. Maybe we're not alone, but we're isolated. Each civilization confined to its own star system, unable to reach the others. That's a sobering thought. Now, I want to be clear about something. I'm not saying that interstellar travel is impossible in some absolute sense. I'm saying it's impossible with physics as we currently understand it and with technology that's even remotely foreseeable. Maybe in 1,000 years our descendants will figure out something we haven't thought of. Maybe there's some aspect of physics we don't understand yet. Maybe quantum mechanics or some other area holds the key. But for now, for the next 100 years, for the next 1,000 years, interstellar travel is not happening, not for humans. The distances are too vast. The energy requirements are too enormous. The dangers are too severe. And the time scales are incompatible with human life. What we can do, what we should do, is send unmanned probes, robotic explorers, machines that can survive the journey and report back what they find. That's achievable. That's realistic. And that's still incredibly valuable scientifically. We can study the planets orbiting nearby stars. We can look for signs of life. We can satisfy our curiosity about the universe without requiring that a human being actually travel to another star system. I think that's actually more reasonable. I think that's actually wiser, because the universe is big enough and fascinating enough, and we can learn enough without killing ourselves trying to physically reach for the stars. The stars are beautiful, they're inspiring, but they're also very far away. And sometimes the most interesting thing you can do is acknowledge that limit, understand it, and work within it, rather than endlessly fantasizing about overcoming it. That's what I think when I look up at the night sky. Not, I wonder what's out there that we could visit, but I wonder what we can learn about what's out there from right here, using our minds, using our telescopes, using our unmanned machines. And that, to me, is just as romantic, just as profound, maybe more so. Because the universe doesn't care about our desires. It operates according to its own laws, and those laws are beautiful and intricate and infinitely more interesting than any science fiction story we could dream up.